Good day, students, and welcome to a session on maths. And you can see I call it maths squared. And the reason for that is that, first of all, in maths, mistakes are allowed to happen. Okay? I know as students, you have a lot of pressure from parents, from educators, that you need to do the best you can in maths. And the reason what happens is then you don't want to make mistakes. So what I would like you all to do is remember that mistakes are allowed to happen. The second part of that is that maths stands for maths ability thrives here. So maths will flourish. You will get excited about it if you have the right attitude for that. And that will only happen if mistakes are allowed to happen. All right, so I hope you keep that attitude in mind as we go through this section of work. Today we are going to look at number patterns. In maths, we also call that sequences. Now, just to give you an introduction to this whole subject, Richard Feynman is a famous physicist who talks about patterns. And he says this: nature uses only the longest threads to weave her patterns, so that each small piece of the fabric reveals the organization of the entire tapestry. What does that mean? It means if I understand the basic building block, the smallest piece of it, then I can understand the whole system. And that is very much the case with patterns. And for me, patterns are the fabric of life. Let's look at where we see patterns. We see it in the universe, in the stars. We see it in nature. In biology, you'll see plants that grow the same way, with the same symmetry, the same shape. That is patterns. If we look at the wind, something very different. Look at the shape that the wind creates on the sand. That is also a pattern. And all these things can be reduced to numbers. And this is the amazing thing. Okay, man-made geometry. If we look at all the buildings that we have, going back to Samarkand, and we look at the mosques and things, this is what we have created. These are all patterns, okay? Let's look at why patterns are important. Patterns helps us to understand things. Okay, what do I mean by that? With patterns, we can develop what I call relationships. If I understand what a pattern is, then I can try to understand how does the pattern work. And if I can do that, I can then go and build what I call systems. And systems tells us something a little bit bigger. And with those kind of ideas, I can do something amazing. I can ask big questions. Why is the universe so big? Or how big is the universe? We can do that by looking at patterns. If we understand that galaxies are moving away from each other at an ever-increasing speed, that is the pattern of the universe. That pattern tells us that the universe is really, really huge. The other question of that is, if that is the pattern, at which point do galaxies stop moving away from each other? Do they slow down? Do they carry on moving? Is there a boundary to the universe? So all these questions that physicists ask starts with a very basic idea that if we have a pattern, that pattern, the speed of the galaxies moving away from each other, tells us a whole lot of things. And we can ask those really, really big questions. Okay, so I hope you understand, and I hope you're excited about the fact that when we study patterns, it's not a dry subject. It's not 1, 2, 3, 4, 5, 6. It's a lot more than that. All right, good. There's another one that we are all currently aware of, COVID-19. We can see it across the world. There's a map showing us COVID-19 all across the world. Now, what has that got to do with maths? Everybody now, today, knows exponential graphs. They talk about flattening the curves. What has all this got to do with maths? It starts with a very basic idea. There's a pattern. The COVID virus spreads in a particular way. One person gets infected, infects 2 persons, and 2 people then infect another 2, and that grows. We call that growth exponential growth. Okay, so there's the pattern. How do we take that pattern and make it a relationship? If I look at how the virus grows, that is one thing. If I look at the impact of the virus over time, that means when people get infected and when they get sick, that is a certain point in time, suddenly someone is sick. When they are sick, it's already 14 days later. So suddenly we see a whole lot of people that are sick. So initially we think there is nothing happening, but then it comes up in big numbers later on. And that is exactly what is happening. So when I take a pattern and I relate it to time, I have a relationship. Now I start to understand that this virus is just not something on its own. Over time, it is having an impact on us. And what does that impact look like? We all saw this, flattening the curve, right? Everyone has seen this graph. If you haven't seen it by now, then you're not keeping up with the news. Okay, what does this tell us? When that COVID virus, a whole bunch of people, that exponential relationship I was talking to you about, when that gets to a very high point, that has an impact on us. Our hospital systems are not geared to deal with all those people. So we have to make a plan. Okay? So we're starting off with a very simple idea. What is a pattern? It's a pattern of how that virus spreads. If I try to understand all those things, then I can start to make some decisions. Then I can ask myself, all right, if I know this is what I need to do in terms of the hospitals, they can't deal with all the people, I have to slow down the virus so that the people that are coming to hospital can get the care they need. Okay, so how do we do that? We try to stop the virus. What are we doing right now? We're all under quarantine. We're all in lockdown. That is to slow the virus down. So again, I hope you see that starting from a pattern, we can go to actually doing something in real life. And that is what we're talking about. Okay, coming back to maths again. So we have to start, obviously, with the basic building blocks. The first thing we see in number patterns, what is number patterns in maths? So we give that a name, we call it sequences, okay? And I have an example there on the board for you. 1 minus 6, 36 minus 216. Now, there is a pattern here. And if I look at that, between 1 and minus 6, there's a difference, there's a multiplying that by 6. So 1 times minus 6 will give me minus 6. I multiply it by minus 6 again, I get positive 36. I multiply it by minus 6 again, I get negative 216. So what I'm seeing here is a pattern that is repeating. I am multiplying every number by minus 6. And we call that a common ratio. Okay? So the common ratio is worked out going backwards, the second number divided by the first number. That we call the common ratio. So in this particular number pattern, we have what is called a common ratio. Okay. There's a second example. If we look at those numbers, 7, 10, 13, and 16, we will see that from 7 to 10, I add 3, and then I add 3 again, and then I add 3 again. So what is the number pattern here? We are adding 3 to each number. Okay? So that is another type of number pattern. All right. Now, it is easy to say that I add 3 or I multiply by 6, but can I make a rule? Can I make a formula? And this is where things get a little bit mathematical. Okay. So let's look at these numbers, 1, 9, 24, 49, 81. What is the rule in this number? So if we look at that, I can say 9 looks like a square number, 25, 49, these are all square numbers. So looking at that, these seem to be odd numbers. And these odd numbers are squared. 1, 3 squared, 5 squared, 7 squared, 9 squared. Okay, so I can say that is the rule. I take an odd number and I square it. So the next number will be 9 squared, 11 squared, 121. Next number, 13 squared, 169, and so on. Okay, the second one, 3, 8, 18, 33, 53. That doesn't look like there's any pattern happening there. So we try to discover what is the pattern. So let's start with trying something. So from 3 to 8, I add 5. That sounds right. 8 to 18, I'm adding 10. 18 to 33, I'm adding 15. Then I'm adding 20. So what kind of rule can I make about this number? Each time I add another 5, and I add it to the previous number. So if I look at 8, I added 5 to 8, 5 to 3, the previous number, and I got 8. If I look at 18, I added 10, so 2 times of the 5, plus the previous number, 8, I get 18. So that pattern looks a little bit more complicated. It's not straightforward addition, okay? And so we have a strange looking rule. I'm saying 5, and then in brackets I have n minus 1. So what is the n? The n is telling me the position of the terms. So my first term, for example, is at 3. The second term is at 8. So if I look at n equals 1, where the 3 is, 1 minus 1 is 0. So there is no addition of 5. The first term is 3. The second term, 8, is position number 2. So 2 minus 1 is 1. 1 times 5 is 5, plus the previous term, which is 3, becomes 8. So here we see a different type of pattern. So we can describe our patterns. That is the key thing. We can describe our patterns. Okay. Now, just to get some of the terminology right, because when you work in maths, everything you do has very specific terminology. So let's get that right first. When we talk about the position of a term, n is natural numbers, counting numbers starting from 1, not from 0, from 1. 1, 2, 3, 4, 5. Okay. The terms are whatever the sequence is, whatever the number pattern is. We call those A1, A2, A3, and so on. Okay. Now let's have a look at the rules. The rules we have, for example, 3n plus 5. What am I talking about there? So for n equals 1, position 1, if I put 1 into that equation, I have 3 times 1, 3 plus 5 is 8. So my first term in the pattern is 8. If I put in 2, 2 times 3 is 6 plus 5 is 11, and that is the second term. And that is how I use the rule to give me the number pattern. Okay? There's another rule. A little bit complicated, 2 to the n minus 1. So that's an exponential rule. So if I put 1 into that, it becomes 2 minus 1, which is 1. If I put 2 in there, it becomes 2 squared, which is 4. 4 minus 1 is 3, and so on. So I can take a rule which is a formula and generate a number pattern. If I look at the number patterns, I should be able to go the other way and write the rules. Okay? So having the formula and writing the number pattern is actually very easy to do. You just substitute n, 1, 2, 3, 4, 5, and you get your sequence. Going the other way is a little bit more difficult. So let's have a look at how we do that. So I'm using the same sequence of numbers again. And this is the one that we said had the odd numbers squared, right? Now, how do I build up the rule? Because see, this part is easy. I can say I'm taking the odd numbers and I'm squaring it. But if I want to mathematically say this is the sequence, how do I write these numbers down? Then I must have a formula. How do I get that formula? When I look at these positions, for n equals 1, I have 1 squared. N equals 2, I have 3 squared. That's a little bit crazy. 3, 5 squared. So let me try something else. So I go down and I say, right, let me try 2n. So for n equals 1, in that position, I'm writing 2. So 2 times 1 is 2. If I'm looking at 2, 2 times 2 is 4. 3 times 2 is 6. Okay? So I am now taking those positions and doubling it up. And then if I look at these odd numbers here, what do I see? 4, 3, 2, 1, 6, 5, 8, 7, 10, 9. So I'm subtracting 1. So if I take 2 times the number and I subtract 1, I should get 1, 3, 5, 7, 9. So there is the first part towards getting an answer, right? If I take 2n minus 1, and then all I do is square it. So that was what my formula should look like. Okay, 2n minus 1 all squared. And if you try that out, you should get that sequence. So we play around with this. Okay, there is no hard and fast rule. Nobody tells you this is exactly how we do it. We have to play with the maths, and this is where it gets fun. This is where maths is actually fun, when you actually start to play with the numbers. Okay. As I said, not always easy to do, but very fun, very satisfying if we can do it. Okay? Let's try a couple just to finish off. Find the rule for this sequence. And this looks really, really crazy. 5, 7, 8, then 10, 11, then 13. I think the next number should look like a 14, but I'm not sure. Right? So there don't seem to be anything obvious here. This first number we add 3, the second number we add 1, then we add 2, then it's 1, then it's 2. So it seems all over the place. To try and find a formula for that is not going to be easy. So I can try something. I can say, all right, if I take the odd numbers, the first, the third, and the fifth term, I can see they give me a formula that looks like this, 3n plus 2. And if I substitute that, I get 7, 10, and 13. And then if I take the even numbers, the even positions, and I do the same thing, then I get the other sequence. So I end up with 2 possible sequences. All right, so I have 2 rules which work, but the problem is, and this is where mathematicians are also, they're crazy people. They want one formula for everything, okay? So how do we find one formula? Right, I'm going to leave that there. That is for you guys to have a look at and see if you can get that right. So this is part of the challenge. This is part of the fun of maths, to actually take something like this and see if I can find that. All right. There's another problem that we look at. This sequence here is one of the most famous sequences in the world, and it has a name called the Fibonacci sequence. Everybody would have heard about Fibonacci. What it means, what it does, what the formula is, nobody seems to know, all right? But it's there, and if you're interested in maths, you go and Google Fibonacci, there's a whole lot of things. This is a sequence that describes how life happens, how things grow, how populations multiply, how flowers actually develop, and how the spiral in the flowers and the number of leaves, all those things follow this strange sequence here. So it's a very, very powerful sequence. It's something to just whet your appetite. Go look it up, Google it, and have a look at this. And I hope at the end of all this, you have an appetite to say, I want to learn more about number patterns. Okay? The next time I see you, we will talk about arithmetic sequences and geometric sequences. And that is the starting. We're going backwards again. We started very high level. We spoke about how number patterns become relationships, become big questions. Now we're going to go back and look at number patterns and build up the theory. I hope you enjoy that. Thank you very much.